In today's video, we will use a coupled inductor instead of inductor. A coupled inductor is nothing but a high frequency transformer generally made of ferrite magnetic material. Hello people and welcome to Electronics for All. This is a channel where we will design and develop industrial grade electronic systems. For every system or a circuit, we will start with basic fundamentals or textbook explanations. In the second step, we will confirm the functionality via simulations and calculations. This stage will progress into development of a prototype. The prototype will then be subjected to rigorous testing to prove its ruggedness. So you will get a walkthrough of electronic systems developments with best industrial practices. So let us start. In the previous video, we observed that the current profile for an inductive load when connected in series with a MOSFET triggered by PWM pulses. We saw that the inductor current is maximum at T on and increases in linear fashion while the current is negative when switch is turned off. In today's video, we will use a coupled inductor instead of inductor. A coupled inductor is nothing but a high frequency transformer generally made of ferrite magnetic material. They are much lighter and compact than the traditional transformers as they work on high frequency, and they also provide galvanic isolation between primary and secondary sides. Let us start with the MATLAB simulation. We will open the previous Simulink model. More components will be added to this model, so let us make it cleaner using goto tags and from tags. These tags will greatly improve visibility and hence understanding. We have used three go-to tags here. PWM tag is for pulse width modulation, Li tag will be used for inductor current, and VL tag indicates the inductor voltage. A go-to tag is always paired with a from tag. This means that a signal which goes into a go-to tag comes out of the from tag of same name. Hence, same PWM signal which goes into go-to tag comes out of the PWM from tag. It can be seen that the visibility and cleanliness has improved greatly, so that if more components are added to this model, then it won't look clumsy. Let us run the simulation and check the waveforms. We can observe that the waveforms are identical as they were in the previous model of MOSFET with inductive load. We will now replace the inductor with a linear transformer. Change the unit system to SI and update the parameters as shown. We will also disable the tertiary winding. Now double click on the MOSFET and change its RDS1 to 100 milliohm. From the pulse generator, we will change the duty cycle to 30%. Let us connect the transformer and arrange all the components properly. Let us add a resistive load of 100 ohms across the secondary side of the transformer. To view the secondary side or output waveforms, we will add voltage measurement block and connect current measurement block in series with the resistor. We will use go-to tags to organize the model. IO tag will be used for output current and VO tag will denote output voltage. Now we have total 5 waveforms to view: the PWM signal, input voltage, input current, output voltage and output current. To change the number of axes in scope, double click on it and change the number of input ports to 5 and make the connections. Oh, so we have done a mistake here. Output voltage tag should be VO, not VI. Let us run the simulation. We can only see 3 axes. Select proper layout for scope axis to view all the waveforms together. We can observe that voltage waveforms are same. Let us remove VI so that all the waveforms can be visualized together. Now change the axis to 4 and change the layout and run the simulation again. There appears to be some problem. The second axis shows no waveform. Let us close the scope and check our connections. So the connection of the scope is broken. Make the connection proper and again run the simulation to view all the waveforms. The first one is PWM signal, second is input current, third one is output voltage and the last one is output current. As soon as the switch is turned on, the current in the primary side rises linearly and reaches maximum at T on. During this time, the energy is stored in the transformer and some energy is transferred to the load. When the switch is turned off, the stored energy is transferred to the load, but there is a change in the direction of the current. Hence you can see the current waveform going negative in the scope after turn off. You can see that the voltage and current waveforms are identical in shape. This is because the load is resistive. We will explain these waveforms clearly in the next video. In the next video, we will achieve the actual output waveforms as they should be in a practical flyback converter. We will stop today at this point and will take it further from this point. Thanks for watching. Drop a like if you found this video helpful. Leave a comment if you have any query regarding the topic. And don't forget to subscribe and share this video with others.